Greetings everyone. I've got another example problem for you today. This one is going to be an elastic collision, and this covers slides 30 and 31 from the 113 Momentum 01.pptx set of slides. First, we're going to do it exactly as you see it in the slides, and then we're going to do it again with different input values so that you can see what changes. This one is going to have some algebra to it, so pay attention to all the algebra and see what tricks we use to solve this problem. Slide 30 in this set of slides says that two billiard balls of equal mass strike each other. Before the collision, one ball had a velocity of 3 meters per second east, and the other was at rest. Find the final velocity of the two billiard balls. And remember, this is an elastic collision. It says so at the top of the slide. And so we need to remember that energy must be conserved. Well, we've seen this before. We know that delta E is equal to 0 because energy is conserved in this one. But this is also a collision. And so we need to remember that delta P is equal to 0, aka P initial is equal to P final. Well, let's start with this one. Let's start with the new stuff. Momentum initial is equal to momentum final. Well, the initial momentum is going to be the momentum of all the things at the beginning of the problem. Well, all the things at the beginning of the problem, well, there's just two billiard balls. So we have to figure out the momentum of the two billiard balls put together. That's going to be the momentum of, well, let's see, what should we call them? If there's one billiard ball hitting another billiard ball, I guess we can name them A and B. So this is momentum of A initially plus momentum of B initially. That's going to be our total initial momentum, just the two momenta put together. Our final momentum will be momentum A final plus momentum B final. What do we know? I guess we know that two billiard balls of equal mass strike each other. Before the collision, one ball had a velocity of 3 meters per second east, and the other one was at rest. I guess A has to be the one with 3 meters per second east to hit B, and B must be at rest. V is equal to 0. V initial for that one is equal to 0. Well, that means that the momentum initially is 0, so that's going to simplify things very slightly. We can plug these in up there. P initial, P final. P initial is going to be momentum A initial. P final going to be momentum A final plus momentum B final. Now we can replace those with mv. Mass of A, velocity A initial is equal to mass A, velocity A final plus mass B, velocity B final. It does say in the problem, two billiard balls of equal mass strike each other. Therefore, MA is equal to MB. We can divide both sides by that M, whatever it is, and get rid of all that. Now we've got VA initial is equal to VA final plus VB final. Okay, well, that's really all we can do. Oh, I guess we can say that VA initial is 3. 3 is equal to VA final plus VB final. Now, I guess that's all we can do. Well, let's move on to the other equation that we have. This was for momentum over here, and here we're going to have for energy conservation. So this is going to be energy initial is equal to energy final. Energy initial, we're going to do the same kind of thing as we did before. Energy initial is equal to the energy of ball A initially plus energy B initially. Energy final will equal energy A final plus energy B final. And same logic, energy B initial has got to be 0. Now we can just plug these in to our initial and final energies. and we get that energy A initial is equal to energy A final plus energy B final. We can plug in our equations. What kind of energy is it? Actually, you tell me. What kind of energy is that? Okay, kinetic energy. We've got 1/2 ma VAI squared is equal to 1/2 ma VAF squared plus 1/2 mb VBF squared. If the masses are all the same, then we can divide everything by mass, and we get to get rid of that, and that, and that, and we are left with VA initial squared is equal to VA final squared plus VB final squared. We can also input the initial velocity there and say that, let's see, 3 squared is 9 is equal to VA final plus VB final and squared. Now at this point, the algebra becomes kind of tricky and very lengthy. And you know me, I like to be kind of lazy, so I'm going to teach you a way of solving this without doing a tremendous amount of algebra. And what we can do to solve that is to just start trying out numbers. So let's save our values that we have there and our equations, and let's start trying out numbers. I'm going to say, how about that VA final, I don't know what it's going to be. Maybe it's going to be 1 meters per second. So we'll try it. We'll try it in this equation first. 3 is equal to 1 plus VB final. Well, okay, VB final would definitely have to equal 2, if that's true. Okay, let's plug in the values that we have guessed into this equation. Well, that's going to get us 9 is equal to VA final. If that's 1, then this is still going to be 1, plus VB final. If it's 2, that's going to be 4. Oh, well, this isn't going to work because 9 does not equal 5, so it's definitely not 1 or 2. Well, if we changed it to 1.5, would that work? Instead of 1 and 2, how about 1.5 and 1.5? Maybe they just kind of share the velocity like that. So, okay, 3 is equal to 1.5 plus 1.5. That would make sense. Okay, 9 is equal to, oh, what's 1.5 squared? Well, let's get our calculator out. 1.5 squared is 2.25. If we do that again, times 2, oh, 4.5. That doesn't get us where we want to be either. That actually gets us even farther away. We've got 9 is equal to 4.5 now. That's not right. Okay, well, let's try another guess. When we had 1 and 2, we had 9 is equal to 5. When we had 1.5 and 1.5, we had 9 is equal to 4.5. Maybe we should try something in a different direction. What if VA final is equal to 0 instead? Well, that would imply that VB final would have to equal 3 from this equation. So is that going to work in this equation? 9 is equal to VA final, 0, plus VB final, 3 squared, 9. Oh, hey, that works. Yeah. So sometimes you have to try something out and solve for it that way. And this is kind of an easy example. You could just plug in 0 in there and get the right answer up there. What does this imply? This implies that if you have 2 billiard balls, now these aren't billiard balls, this is actually what they have instead of sand on a lot of the beaches of the United Kingdom. I picked these up in the United Kingdom when I was there many years ago. So yeah, they don't have sand there sometimes. Anyway, you've got 2 billiard balls. You've got A and you've got B. And so A comes in, hits B, and B goes out, and A stays still. So if A had an initial velocity of 3, and B had an initial velocity of 0, at the end of the problem, after they've hit, A has a velocity of 0, and B has a velocity of 3. B got all of the kinetic energy and all the momentum from A during the collision. Now, this is all going to change wildly if the two objects have different masses. So let's do this problem again with one mass having a one object having a mass of 3m, and the other one has a mass of just m. And let's have this one coming in at 2 meters per second, say, and this one has a v of 0. And then they collide. So that's going to be this one coming in and colliding with this one, and we want to see what happens after they collide, like that. Now, this was not an elastic collision, that was an inelastic collision, and we'll talk about what fundamentally causes the difference between an elastic and an inelastic collision in the next set of slides. Anyway, for now, let's solve this. This is going to be elastic again, and so we need to remember that momentum initial is equal to momentum final, which is true of every single collision in the universe. And we also need to remember that delta E is equal to 0, aka E initial is equal to E final, which is true of elastic collisions only, where energy is conserved and you get the same kinetic energy at the end of the problem that you had at the beginning of the problem. Okay, let's look at this. Momentum initial is equal to momentum final. Well, this is going to be momentum initial is going to be the, we'll call this A and B again. It's going to be momentum initial A plus momentum initial B, momentum final A plus momentum final B. If the initial velocity of B is 0, then we can disregard that and say that momentum initial A is equal to momentum final A plus momentum final B. And we can say that mass of A velocity initial A is equal to mass A velocity final A plus mass B velocity final B. And then we can plug in the difference in mass. Well, how are we going to do that? We're going to say that the mass of A is equal to 3 times the mass of B, which you can see there. That has to be true. This is 3 times more massive than that. That has a mass of 1m, that has a mass of 3m. So the mass of A has to be 3 times the mass of B. I'm going to just plug that in right there. And actually, yes, I'm going to plug that in right there. And so we've got 3m, I'm going to just call it 3m, replace the mb's with m's. 3m v initial A is equal to 3m v final A plus m v final B. And one last thing, I can replace the v initial A with 2 meters per second. So now I've got, oh, and I can take out those m's. So this is going to be 3 times 2 is equal to 3 v final A plus v final B. In other words, 6 is equal to 3 plus v final A plus v final B. Okay, can't do anything more with that. Got to move on. And we'll move on with the energy. Energy initial is going to be the energy of A initially plus energy B initially, but that's going to be 0 because it's standing still at the beginning. Energy final is going to be the energy final A plus energy final B. And then we can just say that energy initial A is equal to energy final A plus energy final B. 1/2 m A v initial A squared is equal to 1/2 m B v final A squared plus 1/2, oh, that's not a B, that's an A. What am I doing? Mass B, there we are, v final B squared. The 1/2s go away because there's 1 in every single term. And we can replace the MAs with 3 MBs, 3 M's. V initial A squared is equal to 3M V final A squared plus M V final B squared. The M's go away again, and then we can replace the V initial A with 2. So 2 squared is 4. That's going to be 12 is equal to 3V final A squared plus V final B squared. And with this, we've got 6 is equal to 3V final A plus V final B. These were the two equations that we were left with on the previous sheet of paper. So let's go ahead and solve them. It's not actually going to be that bad, trust me. So let's solve this first one for V final B and see what that gives us. If we solve that for V final B, we get V final B is equal to 6 minus 3 V final A. And now let's plug in this V final B in there and see what we get. 12 is equal to 3 V final A squared plus 6 minus 3 V final A all squared, and we get 12 is equal to 3 V final A squared plus, okay, remember how to do this? 36 minus this times 2, which is 18 times 2, which is 36 V final A, plus this thing squared, plus 9 V final A squared. All right, bunch of stuff we've got. We can combine a few terms. Looks like this and this can be combined, and we get 12 is equal to 3 V final, 36 minus 36 V final A plus 12 V final A. That's what I was wanting to do. And now, oh, look at this. Everything is divisible by 12. So I'm going to divide everything by 12. We get 1 is equal to 3 minus 3 V final A plus 4, plus just V final A squared, excuse me. Then we can subtract 1 from both sides. We get 0 is equal to, I'll rearrange a little bit, V final A squared minus 3 V final A minus 2. And then we can do some quadratic formula. And so we need negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative b, negative 3, plus or minus the square root of b squared minus 4 times a times c. Oh, that's supposed to be a plus, excuse me. 3 minus 1 was a positive 2, all over 2 times a, which is 1. And so this is going to equal 3 plus or minus the square root of, let's see, 9 minus 8 square root of 1 over 2. So that's just 3 plus 1 or 3 minus 1. And so 3 plus 1 is 4 over 2. 3 minus 1 is 2 over 2. So this is actually just 2 or 1 meters per second. Okay. Well, we got 2 answers out of this. And I don't know which one to pick offhand. 2 meters per second or 1 meters per second? Well, let's go back and look at our original setup, and maybe that's going to help us. Something like that. Here's our original setup. A 3M ball hits an M ball the 3m is going at 2 meters per second, and it hits something going at 0 meters per second. And we were solving for, what were we solving for? We were solving for V final A. These are all steps you can do in your head when you are solving this kind of problem. We want to know what the final velocity of A is. Well, the initial velocity was 2. Does it make sense that the final velocity would also be 2? What would happen then? What would happen if the final velocity of A was 2? We can look right back up here and see immediately if we plug in V final A is equal to 2, right up there, then we get 6 is equal to 3 times 2 plus V final B. 6 is equal to 6 plus V final B. V final B would have to be 0 in that case. So, if V final A is 2, V final B would have to be 0. Or, okay, let's look at the other case. Let's plug in 1 for V final A. Plug in 1 up there. 6 is equal to 3 times 1 plus V final B. So 6 is equal to 3 plus V final B. So that means V final B is equal to 3 meters per second. Now, which one makes more sense? That before the collision, they're at 2 meters per second and 0 meters per second, and after they're at 2 and 0? Or before they're at 2 and 0 and after they're at 1 and 3? If they have the same final velocities as initial velocities, what does that mean? To me, it means that they did this. And they didn't even hit each other. If the final velocity is equal to the initial velocity, they probably didn't actually hit each other, unlike that. They probably just went right by each other. That's the only way to have the final velocities equal to the initial velocities. So I think that it has to be this second option right there to solve it.